Now that we've discussed the AL systems, in which electrons are conjugated over 3 different atoms, what if we were to extend that thought process to 4 atoms? How would this change the molecular orbital description? Well, that's what happens in dienes. 1,3-butadiene is this system right here. And it exists in 2 different forms. We call this one here the S-trans form. And then by rotating around the central carbon-carbon bond, which is in equilibrium, we can get the S-cis form. Now the S-cis form is slightly higher in energy than the S-trans form because you've got some steric clashing between the 2 hydrogens here. And so because of this steric clashing, right, this one is 2.8 kcals per mole higher in energy. But one peculiar thing about 1,3-butadiene is that there's restricted bond rotation around the C2-C3 bond. Right? So if I'm going to say that this is carbons 1, 2, 3, and 4, there is restricted rotation around that C2-C3 bond, so it can't just rotate freely. Now this is odd, since there's actually normally free rotation around the sigma bond, right? There's just a single bond there, right? Well, maybe there's something similar going on to things like DMF, which is a massed allyl system. So if butadiene is really just 2 isolated double bonds, there should be free rotation around that bond. But because there's restricted rotation, somehow these bonds are interacting with one another. You can kind of think of them as communicating with one another. So what we need to do is we need to look at the molecular orbital description of 1,3-butadiene and see if we can explain why there's restricted rotation around that C3 bond. So let's do that. Okay, here's the molecular orbital description for 1,3-butadiene. So again, I've got 4 carbon atoms, so I'm going to have 4 new molecular orbitals. So this is C1, C2, C3, and C4. We're going to construct those molecular orbitals like we did before. In the lowest energy molecular orbital, we're going to have no nodal planes. And so it's going to look just like this, where the 2 central atoms are slightly higher in size, slightly greater in size than the outer 2. So there's your wave. As you move up in energy from psi1 to psi2, let me just label them all, you're going to increase the number of nodal planes. And so the nodal plane in the second system will be immediately in between C2 and C3. And so because of that, you're going to have a system that looks like this. And as you cross the nodal plane, you're going to change the phasing. Now the way we've drawn this here actually resembles the butadiene structure. So if we look at butadiene, right, the butadiene has the 2 pi bonds here or here. And so this kind of resembles the way we draw the Lewis structure for butadiene. But for now, let's just worry about the molecular orbital description. As we move up, we're going to increase the number of nodal planes, and so the new system will look like this. Here's our wave. And again, it's going to be symmetrical with respect to the vertical direction, and so you've got these 2 on the outer are going to be bigger, but as you cross the nodal planes, of course, they're going to change the phasing. And finally, there's going to be a node in between each of the carbon atoms. And so there's our wave again. And then this system will look a lot like psi1 in terms of the size of the orbitals. But as you cross the nodal planes, you're going to change the phasing once more. Okay, so we have 4 different wave functions to describe the 4 different molecular orbitals. Now we need to start adding in electrons. So again, remember that butadiene has 4 electrons total, and so we need to add in the electrons here. So we're going to add from bottom to top. There's 2 there, and there's 2 there. Right? We say that this bottom one is the pi 1. This is the pi 2. This is the pi 3 star, and this is the pi 4 star. Okay, we can identify the HOMO and the LUMO here. The HOMO is going to be pi 2, and the LUMO is going to be pi 3 star. And then, of course, we have the nodes. 0 nodes in psi1, 1 node in psi2, 2 nodes in psi3, and 3 nodes in psi4. Okay, so now the key difference here is that if you look at psi1 and psi2, you might notice that the size of the bonding interaction in psi1 between C2 and C3 is stronger than the antibonding interaction between C2 and C3 in psi2. So the way that these molecular orbitals are, the way the size of the orbitals change from bottom to top helps us explain why there's restricted bond rotation around this carbon-carbon bond C2-C3. All right, so let's take a look at C2 and C3. So here's C2 and C3 in psi1. Here's C2 and C3 in psi2. Okay, so there's a strong bonding interaction in between C2 and C3 in psi1. And there's an antibonding interaction between C2 and C3 in psi2. However, the size of the bonding interaction, the size of these 2 lobes, is greater than the size of these 2 lobes. So you can kind of think of this as the antibonding interaction between C2 and C3 that exists in psi2 doesn't fully cancel out the bonding interaction between C2 and C3 in psi1. So this means that there's net bonding between C2 and C3. If there's net bonding between C2 and C3, that can explain why there's restricted rotation, right, between C2 and C3. This should make sense why the barrier to rotation exists between the S-cis and the S-trans. Now this can only happen if the size of the coefficients are different. And so there's a mistake that is made in many textbooks to try to explain this by equating all of the size of the orbitals. So if this was the case in psi1, and this was the case in psi2, there would be equal antibonding interaction with bonding interaction. They will cancel out fully. And so this is not the case, right? You'll find this in some textbooks. It is the case that because of the wave-particle duality of an electron, this makes the central 2 atomic p orbitals, the central pi system, larger in psi1 and smaller in psi2. Now, besides restricted bond rotation between C2 and C3, there's another reason why this is important. let's say, let's kind of ask the following thought question. If butadiene were to act as a nucleophile, it would react via its HOMO. So if it's reacting via its HOMO, we have to ask ourselves, okay, which carbons are going to react? Because there's 4 of them. And what you'll notice is that the ones that react are going to be the ones on the ends because they have the greater coefficients. They have the greater electron density. You can kind of say the same thing for an electrophile. If butadiene was acting like an electrophile, it would react via its LUMO. And so that means it's reacting via Psi3. Where would it react? Which carbons would react? Of course, it would react on the ends because that's where the greatest electron deficiency is. And so this all stems from the fact that you can't describe the molecular orbital description of 1,3-butadiene without taking into account the wave-particle duality of an electron. This is a very key thing in understanding butadiene. Okay, so let's talk a little bit more about the effects of conjugation in these types of systems. What would happen if you had more and more conjugation? Okay, so let's describe what would happen if you have more and more conjugation. So conjugated systems have greater stability than non-conjugated systems. Okay, so let's say we take that system versus this system. Right, this system is a conjugated system, and so it's more stable. And the reason it's more stable is because Psi1 is lower. This is a non-conjugated system. It's almost like you have 2 independent pi systems, 2 independent double bonds that are not talking to one another. And so because they're not talking to one another, they're not interacting, their energy is going to be slightly higher. What's another effect? Well, I should say one more thing, that this idea of conjugated systems having greater stability than non-conjugated systems, this is a thermodynamic effect. Second thing, conjugated systems are more nucleophilic than non-conjugated systems. In addition, conjugated systems are more electrophilic than non-conjugated systems. But let's focus on nucleophilicity for a second. Right. This is a kinetic effect. I'll just put electrophilic in here as well. So conjugated systems are both more nucleophilic than non-conjugated systems, and conjugated systems are more electrophilic than non-conjugated systems. And this is a thermodynamic, this is a kinetic effect. The LUMO of conjugated systems is lower than non-conjugated systems. So it more readily accepts or reacts with a nucleophile. Right? It's more electrophilic. Right? By the same token, the HOMO of conjugated systems is higher than non-conjugated systems. Right? So it more readily reacts with electrophiles. Right? Again, it's more nucleophilic. Next thing that's important. As you add more and more conjugation, the HOMO goes up. This is a kinetic effect, it's more nucleophilic. The LUMO also comes down. But the psi1 always goes down. This is a thermodynamic effect. It's more stable. This is the essence of UV-Vis spectroscopy. In UV-Vis spectroscopy, you have electronic transitions. Right, so in electronic transitions, we're promoting an electron right from the pi bond to the pi star. Well, if our pi system that's the HOMO, and the LUMO is the pi star, and the HOMO has increased, and the LUMO has decreased, what will happen is that the increasing conjugation will lower what we call the HOMO-LUMO gap. So the HOMO-LUMO gap is the difference in energy needed to promote an electron from the pi to the pi star. Right? So the HOMO-LUMO gap is the wavelength, energy needed, right, to promote the electronic transition. All right, so if the increasing conjugation lowers the HOMO-LUMO gap more and more and more, that wavelength needed to promote the electronic transition gets longer. Right? E equals hc, or equals h nu, which is equal to hc over lambda. So as energy gets higher, as energy gets lower, as the HOMO-LUMO gap decreases, lambda increases. And eventually becomes so long that it occupies the visible region of the electromagnetic spectrum. Right, and so this is the reason for why you have color, why we see color. It's the reason why we have color on leaves in the fall. And that's because of the conjugated dienes that exist in the leaves themselves, in the tissues of the leaves. And so one of the molecules that's in those leaves is lycopene. And so I'll draw lycopene out here. And what you'll see is that it's a conjugated system. And And so because we have a very, very extended pi system right here for lycopene, this is going to lower the HOMO-LUMO gap as the energy that's required to promote an electronic transition decreases. Right, that energy goes down. The wavelength that's needed to promote that electronic transition increases. And so all of a sudden now the lambda max is in the visible region. And so this is lycopene and carotene. This gives rise to the orange and red and yellow colors of leaves. Now the final point about dienes activity. So dienes react with electrophiles for example, HX or X2, like any normal pi bond. But the intermediate carbocation can undergo resonance stabilization. And so there's a possibility of getting two different products. So we call those products the 1,2 addition or 1,4 addition products. Right, let's take the example of a 1,3-butadiene reacting with HX. Let's just say it does an electrophilic addition. And so we get addition of the pi bond, right, to give us a carbocation right here. That carbocation can undergo resonance delocalization. And as it does that, we generate a new carbocation. Now those two carbocations are or could potentially react to give you a product. So X minus could come along in each of those cases to give you different products. And let me actually use a blue arrow here. And so in the case of this one, in which we're getting the X addition at that position, we call this the 1,2 addition product. Because if we're saying that this is carbons 1, 2, 3, and 4, the HX is adding across the 1, 2 positions. Right, in the case of the second one, if X minus attacks that that last carbon there, we're going to get this species. And we call this the 1,4 addition product. Again, because you've added the hydrogen to the one position, it does resonance delocalization and then gives you attack of X minus onto the fourth carbon. Now, how can you control whether you get the 1,2 or 1,4 addition products? The 1,2 addition product is a kinetically controlled product. It forms the fastest, and so you want to do this under cold temperatures. Cold temperatures, short reaction times. By contrast, the 1,4 addition product is under thermodynamic control. And so this gives you, this is the more stable product. So this is, it's a more stable product because you have a di-substituted double bond. This happens when you have higher temperatures and longer reaction times. And so this gives you a brief introduction to dienes, and what we're going to talk about in the next section is a key reaction of dienes, and that's the Diels-Alder reaction.